Dear students, welcome to our first lecture on the topic of mathematical foundation of machine learning. On the videos that I have uploaded on my YouTube channel dealing with linear regression or maximum likelihood estimates, we have tried to balance theory with mathematics as well as implementation. And you might have noticed that certain concepts are very cumbersome and heavy on notations, but as soon as we get to understand what they really mean in the context of data, life becomes much easier. Now, through series of these videos, I will try to drive the message home that when we deal with various machine learning concepts, the mathematics behind it is equally important to understand, implement, and innovate in various aspects of data sciences and machine learning. With the advent of platforms like TensorFlow or Keras, while the implementation of various algorithms have become much easier, the underlying mathematics still is very frightening for many of us as it is full of notations. However, when we talk about applied sciences, specifically earth sciences or atmospheric sciences, and we are interested to know the data, we may have to read certain research papers or certain articles where notations are typically used. Now, through these lectures, we will try to get good hold of those concepts. We will try to understand how they are applied in a real world. But before we go there, we will not jump the guns and we will try to understand these things very fundamentally so that it makes sense when we see the notations. The two key objectives that we will try to attain after doing or developing some good mathematical understanding would be in the area of dimensionality reduction and clustering slash regression. So if we understand these three pillars, that would mean that we will understand the application of machine learning to solve various data problems very easily. Within dimensionality reduction, we will talk about methods coming from principal component analysis as well as singular value decomposition, and then we will also talk about what is the curse of dimensionality through both examples motivated from earth sciences as well as non-earth sciences or other domains of life. But this curse of dimensionality would be a big thing when we step into data sciences, that why we really want to avoid large dimension data set, what these dimensions actually even mean. So let us get started and try to understand what are the various things that we will try to solve through these examples. Now, many of you might have heard of online streaming services such as Netflix or Amazon Prime or any other Hotstar and such. Now, whenever you watch a movie on Netflix, the platform typically asks you that on scale of 5, how would you rate the movie? Some of you say 3 out of 5 for one movie. So this is movie 1, this is movie 2, you liked it. So you are a big fan of sci-fi movies. You say, oh, I really loved it. This is 4 out of 5. Similarly, you watched Mth movie, movie M, and you say that since this is a romantic movie, I really don't like these kind of movies, so I'll just give it 1 to 5. And there are thousands of movies. You are not going to watch every movie, but you will try to give rating to a few that you have watched. You will also skip rating to those which you have watched, but on an average you will give the sparse rating. Not everybody would be rated, but we are assuming that whatever rating you are giving, it really reflects your opinion about that particular movie. Now, there are hundreds and millions of users who are watching Netflix, and there are hundreds and thousands of movies on the Netflix. So, if we put this particular information in some data structure, we will talk about how to represent this data, where let us say that rows represent number of users and column represent number of movies. And if we have 1 million users and Amazon has 2000 movies, you can quickly imagine that the number of elements that we need to represent this data would be 1 million times 2000, which is already of the order of 10 to the power 9. And this is typically we call as this is a good example of a high dimensional data set. Now, one of the problem with high dimensional data set is that high dimensional data set, they are often over complete. And what this overcomplete means, that the information that is present in this high dimensional data is often redundant. For example, you are watching a movie on a 4K television versus a 1080p or a full HD movie. The content or the kind of images that you are getting to see on an average would not differ significantly. However, the amount of storage that you would need to store the same message that the movie or a clip or a documentary is conveying, it will take a lot more information as compared to a typical standard definition or full HD movie. However, for your satisfaction that you really enjoy, you are fascinated by a 4K movie, by cool graphics, that is often a case that you would be making some extra investments. But on an average, you would say that yes, the information is over complete when we are talking about high dimensional data set. Similarly, if you really like a sci-fi movie, does not matter you watch 100 movies, 100 and 1000 movies or 1200 movies, if you really convey by liking 50 or 60 odd movies from a sci-fi category, you have already conveyed the interest that yes, I like the sci-fi movies and that's why I'm liking them. Now, if you put data for all the movies, sci-fi movies that have been created, you are creating an over complete data of the preferences. Now, as you are creating an over complete data, the size of data will increase and hence storage will become very difficult. Storage is difficult and you would need to make some significant investments to store lot of high dimensional data set. Another issue that arises is the visualization. Now imagine that you are in a two-dimensional data space where you have to plot certain vector. We will talk about what we call as vectors, but let us say that vector is something that has a magnitude as well as a direction. On a two-dimensional data set, you can easily plot it. Now if I say that, let us assume there is a three-dimensional data set and you want to plot a vector in a three-dimensional space. This is not as easy as a two-dimensional space, but you can still visualize it in terms of your room or where you are sitting, and you can say that okay, if I have to plot a three-dimensional data set, let us say this is an origin, I can still plot it, right? Because this is something you have been trained to think that you can plot two dimension, you can plot three dimension. But now let us change the problem a bit. I say that now you are given a four-dimensional vector, and a four-dimensional vector has some numbers 1, 3, -1, 4, 6, and it may represent that certain coordinate of a particular object with respect to the origin, and we say that this x belongs to the four-dimensional real space. So this is the notation that we will typically use. So this is a symbol for vector, it belongs to R or a four-dimensional space. Now, plotting this would not be possible on a piece of paper. You either have to take projections or you have to come to the lower dimensions or plot two dimensions at a time. And that clearly drives the message home that yes, indeed, working with high dimensional data set really impair how we visualize a particular data set. And if visualization is hard, interpretation also becomes hard. Now, if I say that what you can interpret with this, you can quickly say that if you talk about two-dimensional data set, I can say that yes, it is a displacement from the origin and I can plot it and it is easier to interpret. Similarly, if you tell me that there are three movies, I like movie A, B and not C, I have only seen limited dimensions and I can say that okay, this movie is a romantic movie or a sci-fi movie, and it clearly tells that what is your preference. So these are some of the curses that we deal with dimensionality, and also to represent or encode this dimensionality into the models, we typically have to set up very complex machine learning models. And when we talk about complexity of machine learning models, we are talking about large parameters. And when we go to deep learning, we are typically talking about parameters in the order of thousands or sometimes hundred thousands, right? And this is not desirable, because if you have more parameters, that would mean more parameters to calibrate, and sometimes there are chances that we also run in the troubles of overfitting if we are really going with the highly complex models. So with all these challenges, we need to reduce the dimensionality, that, and we will learn that what this dimensionality reduction entails, how to achieve that, and why it is so popular in field of data sciences and machine learning. Now when we talk about dimensionality reduction, we say that we want to compress the data set, and we want to compress the data set in a way that the information loss is minimal. For example, you have an image that you want to send over Gmail or any other email service. Now, when you compress that particular image, that means you want to reduce its size, but you still want to look as if you are sending your passport size photograph, you still want to resemble a person who you have sent in a passport size photograph via compressed email. So you want a compressor system or any software that reduces the size but keeps the information loss that is happening between original image and the compressed image in minimal fashion. To achieve this in these kind of compressions, we typically use SVD, what we call as singular value decomposition, and principal component analysis. And there are many versions of PCA, for example RPCAs or probabilistic PCAs, but to begin with we will keep it simple and try to understand what is SVD, what is PCA, and how they are implemented. Now also coming to the environmental application. So when we deal with climate data, we are typically interested into understanding certain oscillations. So you might have heard this word called as El Nino, La Nina, Indian Ocean Dipole, and these are typically called as oscillations, where you clearly see that certain patterns are exhibited in space. For example, when we talk about certain oscillations, we say that we have warmer ocean waters in comparison to the surrounding land, or vice versa, or the patches of these warmer waters in the ocean shifts, but we say that the pattern is very consistent and it can explain large amount of variability within the climate systems. For example, if you look at climate data, it's a high dimensional data set because you are representing entire globe. Let us say that this is map, this is India, this is US, not so great of a drawing, but just a representation. And here we divide this into number of grid points. And we have this data over a period of, let us say, 100 years. And it's a daily data. So we will have 365 times 100 data points that we have to deal with when we are dealing with the daily data. Also, we are trying to understand this earth by dividing it into grids, and this data is gridded in a sense that each grid is associated with some resolution. So let us say that this information is represented at 25 kilometer by 25 kilometers. Now if you present this information in form of a matrix, this matrix will have a huge size even if you flatten everything. So that would be basically number of grid points in x direction, number of grid points in y direction, and that should be the circumference of the earth divided by the resolution horizontally in both, and similarly the circumference measured along the poles divided by number of grids. So basically these number of grids would be in thousands, multiply by 365,000, and hence this again becomes a very large dimensional matrix. Right now we are using this word dimensionality in a loose sense, but we will define this mathematically, and that will make much more sense that what is this dimensionality is. But right now one thing is for sure, that in a layman language, the size of this matrix is very large, and we say that this is a large dimensional product. Now, lot of this information can be explained in terms of what we call as principal components, that exist in space and time. And we typically use approaches like empirical orthogonal functions and their variants to understand the kind of variability and to reduce these large dimensional matrices into something which is reduced size or small dimensional data sets. We let us say that this is m, this is small m, and we say that small is much smaller than capital M. To achieve all these things without loss of information or by capturing enough of the variance, we would be able to capture the data set. Easier said than done, because most of the algorithms, they will just take in the data, implement it for you and give you an output, which would make sense if you just look on computer screens. But to understand what's going inside the algorithm and to work on that, you have to look into some of the basic concepts of vectors. So we will try to learn and define vector spaces into the context of machine learning, and we will learn about linear dependence, what this dependence means, and finally what is basis and rank of a matrix or the data sets that we deal with, and how we can change the basis, or what we call as define the dimensionalities in terms of basis, so that whenever we say the word high dimensional data set, we are very clear what we are talking about. So these would be the topics that we will deal with in our next lecture. And before we will start our next lecture, we will also fit the various components of mathematics, that what would be required to solve what part of SVD or PCA, so that we have clear idea that why we are going with this lot of mathematics before really writing codes for certain algorithms. Thank you.